SpaceX faces a critical bottleneck, Raptor 3 production. Over a year after the first engine rolled out, only 35 units have been spotted, far short of the 39 needed per flight. The evidence is clear from Starbase observations and source reports. This isn't speculation, it's documented reality. Each Starship mission requires 33 engines for Super Heavy and 6 for Ship. Without rapid production scaling, Flight 12 and the entire V3 program face serious delays, threatening NASA's Artemis timeline. Let's dive right in. The math is straightforward and sobering. In August 2024, SpaceX unveiled Raptor 3 serial number 1. 14 months later, Starbase observers have documented engines only up to SN35. The vacuum variant shows even fewer units. Just 8 confirmed, with SN8 being the highest number Musk has publicly displayed. This translates to approximately 2.5 engines per month. Each Starship flight requires 39 engines total, 33 for Super Heavy and 6 for Ship, including 3 vacuum-optimized variants. At the current production rate, SpaceX needs roughly 16 months to build enough engines for a single flight, assuming every engine passes quality control. The contrast with Raptor 2 development is stark. During comparable timeframes, Raptor 2 production operated at nearly triple this pace. Hundreds of units moved through Starbase facilities, supporting SpaceX's aggressive testing schedule. The supply chain kept pace with demand. Today, that's no longer the case. Raptor 3's design philosophy centered on manufacturability, fewer components, streamlined assembly processes, reduced complexity. On paper, these changes should have accelerated production, not slowed it. Musk publicly stated the goal: multiple engines per day, enabling the rapid launch cadence necessary for sustained Starship operations. Yet production remains constrained. 3 factors could explain this discrepancy. Supply chain bottlenecks represent the first possibility. Specialized materials, high-performance alloys, precision machine turbopumps, advanced metallurgical components might be arriving slower than needed. However, SpaceX has spent years developing supplier relationships and vertical integration capabilities. Raw material delays seem unlikely to persist this long. Manufacturing complexity offers a second explanation. Reducing part count sometimes introduces tighter tolerances or more demanding assembly procedures. What appears simpler in CAD models may require additional precision during actual production, slowing the process per unit even as total parts decrease. Quality control provides the third and most likely scenario. SpaceX may be producing engines faster, but rejecting more units during testing phases. If early Raptor 3 engines revealed reliability issues, performance inconsistencies, structural weaknesses, or operational anomalies, the company would logically tighten quality standards. Better to delay now than experience failures during critical missions. The stakes support this interpretation. These engines will power NASA's Artemis lunar lander, orbital refueling demonstrations, and eventually Mars missions. A single engine failure during any of these operations could derail years of progress. SpaceX has every incentive to prioritize reliability over speed during this development phase. This production constraint directly impacts the V3 debut schedule. Ship 39 and Booster 18, the first V3 prototypes, await final assembly. But assembly cannot proceed without engines. Consider the timeline required even if engines became available today. Ship 39 needs approximately 30 days for complete stacking and integration. This estimate comes from Ship 33's assembly period, the first V2 prototype. Ship 39, featuring upgraded systems and new capabilities, will likely require similar or longer duration. Following assembly, cryogenic proof testing begins. These tests verify tank integrity under extreme temperature stress. Static fire trials come next, validating engine performance and vehicle systems integration. Between each major test milestone, engineers conduct inspections, make adjustments, and install additional components. This testing campaign typically spans 4 to 5 weeks for new vehicle configurations. Final preparations add another week. Payload integration, flight termination system installation, final system checkouts, and rollout to the launch pad. The total timeline from beginning assembly to launch readiness, approximately 10 to 12 weeks under optimal conditions. We're currently in early October. Starting Ship 39 assembly today puts the earliest possible completion in mid-November. Testing through mid to late December. Final preparations into the year's last week. A December 30th launch becomes theoretically possible, but only if every step proceeds flawlessly and all 39 required engines are available when needed. Any delays, a failed proof test, an engine issue during static fire, infrastructure problems, push Flight 12 into January 2026 or beyond. The engine shortage creates cascading effects across SpaceX's ground operations. The Massey's test facility, where vehicles undergo trials before launch, remains partially offline. The Ship 36 incident damaged the ship testing stand, requiring extensive repairs and upgrades to support V3 vehicles. Booster 18 hasn't begun visible testing yet. The most practical explanation: engines aren't available for installation. Without engines, the booster can't perform static fires. Without static fires, engineers can't validate the rebuilt test infrastructure or verify Booster 18 systems. Pad 2 at Starbase faces similar dependencies. Construction continues steadily. Chopstick movements, water deluge tests, component installations. But the pad hasn't undergone its most critical validation: a full-power static fire with Raptor 3 engines. This test is essential. The pad must withstand forces generated by 33 engines firing simultaneously. Extreme vibrations, acoustic energy, thermal stress, and structural loading far beyond Raptor 2 specifications. Engineers need data from this test to confirm Pad 2 can safely support V3 launches. But conducting this test requires either a dedicated test tank or an actual booster equipped with flight engines. Both options demand the same resource currently in short supply: Raptor 3 engines. These delays ripple beyond SpaceX's internal development schedule. NASA's Artemis program depends on Starship as the lunar lander for Artemis 3, the mission returning humans to the moon's surface. The Artemis architecture requires multiple Starship flights working in coordination. Tanker vehicles launch first, carrying fuel to orbit. These tankers rendezvous with a depot Starship, transferring propellant through demonstrated orbital refueling operations. The crew vehicle launches separately, docks with the fueled lander, and proceeds to lunar orbit. After surface operations, the lander returns crew to the Orion spacecraft for Earth return. This sequence demands proven, reliable systems validated through extensive testing. Each component, orbital refueling, precision docking, long-duration propellant storage, lunar descent and ascent, requires multiple test flights to verify. SpaceX needs sustained launch cadence to accumulate this flight data before Artemis 3's currently projected 2027 timeframe. Current engine production rates threaten this schedule. Fewer available engines mean fewer possible test flights. Reduced testing opportunities compress the timeline for proving critical capabilities. Mission complexity remains unchanged, but the time available to validate systems decreases. If Flight 12 slips into 2026, subsequent testing milestones shift accordingly. Orbital refueling demonstrations, scheduled for mid-2026, could move to late 2026 or early 2027. Ship catch attempts, planned for 2026, might not occur until 2027. These delays compound, potentially pushing Artemis 3 beyond its current target date. NASA maintains backup plans. The agency always does, but Starship represents the primary path forward. Alternative architectures would require years of additional development and substantial budget increases. NASA's leadership strongly prefers keeping Starship on schedule. Beyond Artemis, Mars missions face even tighter constraints. Earth-Mars transfer windows open approximately every 26 months when planetary alignment allows efficient trajectories. The next window opens in late 2026. Musk has repeatedly stated SpaceX's goal of sending uncrewed Starship missions to Mars during this window. Achieving this requires proving multiple capabilities beforehand: orbital refueling at scale, interplanetary trajectory precision, heat shield performance at Mars entry velocities, long-duration system reliability, and landing capabilities in Mars atmospheric conditions. None of these milestones can be validated without extensive Earth orbit testing first. Each test flight provides data, reveals issues, and validates improvements. Reducing the number of test flights before the Mars window closes leaves less margin for discovering and solving problems. Missing the 2026 window delays Mars missions until 2028 to 2029. That's not just a schedule slip, it's a 3-year pause in proving Mars-capable hardware. For a company whose stated mission is making humanity multiplanetary, 3-year delays carry significant strategic implications. The long-term solution is clear. SpaceX must achieve dramatically higher Raptor 3 production rates. Current output supports approximately 2 flights per year. SpaceX's stated goals require 12 to 24 flights annually, eventually scaling to weekly or even daily cadences. At 5 engines per day, Musk's stated production target, SpaceX could manufacture 39 engines in 8 days. This rate would enable maintaining deep inventory reserves, supporting parallel programs, and achieving the launch frequency necessary for Starlink constellation expansion, commercial missions, government contracts, and exploration objectives. The gap between current production, 2 to 3 engines monthly, and required production, 150-plus engines monthly, is substantial. Closing this gap demands more than incremental improvements. It requires transformative changes, expanded manufacturing facilities, additional production lines, larger specialized workforce, refined quality control processes that maintain standards while increasing throughput. SpaceX has capital, engineering talent, and proven ability to scale complex manufacturing. The Falcon 9 program demonstrated this capability. The company now produces multiple Merlin engines weekly while maintaining exceptional reliability. Raptor 3 production can reach similar scales, but the transition takes time and focused resources. The next 8 weeks provide crucial indicators. If Ship 39 begins stacking immediately and Raptor 3 sightings increase significantly, December Flight 12 remains achievable. Accelerated activity across Starbase, more engines visible, increased testing operations, rapid infrastructure completion, would signal SpaceX is overcoming current constraints. Alternatively, if Ship 39 remains unstacked through late October, if Raptor 3 production stays at current levels, if Pad 2 testing proceeds slowly, then Flight 12 in 2025 becomes improbable. The timeline simply doesn't accommodate the required work within the available time. SpaceX rarely misses publicly announced launch dates without strong technical reasons. If the company quietly revises Flight 12 expectations, it will signal that engine availability, not vehicle readiness, not pad infrastructure, not regulatory approval, has become the limiting factor. This matters because identifying the constraint allows SpaceX to focus resources appropriately. If engines are the bottleneck, throwing more engineers at vehicle assembly doesn't help. The solution requires addressing manufacturing capacity, quality control processes, supply chain optimization, and production workflow efficiency. Raptor 3 production represents more than a near-term scheduling challenge. It's a fundamental test of whether SpaceX can achieve the manufacturing scale required for its long-term vision. Building a few dozen engines proves design capability. Building hundreds monthly proves industrial capacity. Only the latter enables sustained Mars colonization, routine lunar operations, or point-to-point Earth transportation. The current production rate suggests SpaceX is still in the prove the design phase rather than the scale production phase. This isn't necessarily problematic. Prioritizing reliability during initial development is sound engineering practice. But the transition to high-volume production must begin soon if 2025 to 2026 objectives are to remain achievable. SpaceX has overcome manufacturing challenges before. Falcon 9 production scaled from sporadic launches to weekly cadences. Starlink satellite manufacturing grew from dozens to thousands annually. Raptor 2 production ramped faster than Raptor 1. Historical patterns suggest Raptor 3 will eventually reach required production levels. The question isn't whether SpaceX can solve this problem. The question is when, and whether when aligns with mission-critical timelines for Artemis, Mars windows, and commercial commitments. Here's the bottom line. Raptor 3 production is the real test of whether SpaceX can deliver on its promises. Building one revolutionary rocket is impressive. Building dozens per year, that's what changes everything. The next 8 weeks will reveal the truth. Watch for Raptor 3 engine counts at Starbase, Ship 39 stacking progress, and whether Flight 12 actually launches in December. These numbers don't lie. This matters because NASA's Artemis program, commercial lunar missions, and Mars exploration all depend on SpaceX solving manufacturing at scale. Not just better rockets, more rockets, consistently. So what do you think? Can SpaceX ramp up Raptor 3 production fast enough for a December Flight 12 launch? Or are we looking at 2026? Drop your prediction in the comments. This is Space Hub, where we track the real story behind space development. Not just the headlines, but the hard data that shows what's actually happening. If this analysis gave you new insights, hit that like button. Subscribe and turn on notifications so you don't miss our next deep dive into SpaceX's progress. We're covering every development as it happens. The engine count will tell us everything we need to know, and we'll be watching. Thanks for watching Space Hub. Keep looking up.